Okay. So hello everyone, and as you heard, my name is Jukka Länsineva and I'm from Solita. I'm just going to give you a brief introduction to who we are. If you were at Jere's presentation yesterday, you probably got the most of this. So let's just quickly go through this. Here you can see my picture. I'm a software designer at Solita, and I'm here to tell you a little bit about functional programming. And our agenda for today, quick words about Solita, then we go into programming things, and hopefully we'll have some time for questions and comments later. What we do at Solita, basically, we offer the whole scope of software development, which starts from design, UI design, UX design, business design, designing the processes of our business and so on. And then we offer data solutions, data analytics, and then the basic software development, which we mostly, I think we do mostly web applications. And of course, to back those up, we have cloud solutions, infrastructure, and stuff like that. And then we have ongoing support for all the things we do. We offer that kind of service as well. And our offices are located in, well, around Europe, but most of us are in Finland. We are originally from Tampere, and I think the biggest offices we have, the big three are Helsinki, Tampere, and Oulu. And I'm not sure if the others are coming up, but I'm just going to say it as a fact that Oulu is the third largest of us. We have 82 people around at Oulu, and we are located at I think the best place in Oulu, here at Valkea, where I am currently now. So very good place for finding some good lunches and good after work places whenever we are able to actually go to those kind of places. We have representation of all our units here in all offices, so very wide scope here of people. And especially in Oulu, we work on our own premises. If you have heard of other consulting companies who like to do so-called käsiparikauppa, where you sell people to basically other companies and they join their teams. We do some of that as well, but in Oulu, we are mostly focused on selling project teams and working within our own offices, which I think is great. And here are a little bit of our values. This is our values. So it's, I always feel it's a little bit of a marketing kind of thing, but I can say that of the companies I've been part of, these values come around in Solita more often than perhaps before. So there's some merit to those too. A quick look at some of our clients. As you can see, there's a wide selection of different kind of companies, both in private sector and in public sector. And these are our public references and what we can share. And here's our slogan: we create impact that lasts. And I don't know what it actually means, but it's a slogan. So let's go into the presentation part. Yep. So our topic for today is that functional programming is awesome. And during this presentation, I'm going to tell you a little bit about the functional programming and how we do it at Solita with some practical examples and maybe some tips on how to get started with functional programming and especially Clojure. So a little bit about me. I've been at Solita for 3 years now, 3 years in March. And in the industry, I have been 6+ years, maybe. I'm a Bachelor of Science from Oulu University. And currently, I'm a basically full stack Clojurist. I've also done some Java and just some basic JS professionally with frameworks like React, and I've used Angular and stuff like that. So I have some kind of a touch point there as well. And then on my free time as a hobby, I've also done stuff like Unity and C# and Python and all kinds of stuff like that. But yeah, mostly I've been professionally working on Clojure now. And on my free time, I like to do BJJ and judo. I like video and board games, and I like both the design and the play aspect of those. And drony and bleepy music, making and listening is close to my heart, and basically anything to keep me from finishing my master's thesis at the university. And so yeah, how I started actually, well, games are fun, as we know. I think many of us would agree with that. And I think many people who get into this line of work get so by way of games. They play games, games are fun, they maybe start modding games, and then they might end up writing their own games. And the thing about games in this context is that games are kind of locked into the imperative programming paradigm. And that's just how it has always been. It's kind of de facto standard there. The dominant languages in game development are stuff like, well, maybe not C anymore, but C++. I think Unreal Engine is C++, and then Unity is C#. And then there's stuff like, Java and some others. And so that's kind of where I started and how I got into software development. And the way I got into functional programming then was I was recruited into a Clojure project at my previous employer, and that's been kind of the downhill ever since. So quickly, let's talk a little bit about programming. What is programming really? And it's basically we do computations because we want to achieve some sort of result. And that can be something as simple as summation. For example, we could do 1 + 2 + 3, and we get the result of 6 out of it. But we could also think of it as something like a web application. We read something from a database, and then we process the data we get, and we do those computations there and end up with some sort of a web page that we display to the user. So in this case, we have a value that's the HTML code we end up showing to the user. Or in some case, like a video game, we might look at the game state, we process it and do computations to it, through the game logic, we check which assets we need, and then we do calculations on how they should be positioned and stuff like that. And in the end, we get some value out of it, which in this case would be a frame that we display on the screen. So it's all about kind of like reducing all these things into single value, but the value can be in quite many forms. But yeah, that's basically what we do. And there are two ways about it. Imperative, which I mentioned before, and then declarative. And out of these two, most popular approaches would be object-oriented programming in imperative side and functional programming in declarative side. And those are based on the models of Turing machines and Lambda Calculus respectively. And Turing machines, if you haven't heard, is a model of computation that basically does operations on a state. And this was developed by Alan Turing. And it's kind of like the base model for a lot of imperative systems. And it can be used to model a lot of things. It can be used to model stuff like algorithms and languages and even a CPU, because when you think about it, you know, CPU has all these registers, which are like the state, and you put different things to the registers, and then you make the CPU do different things. And you might have it of Turing completeness, which means in case of programming languages that a language can simulate this kind of Turing machine. And Turing completeness is not limited to programming languages. And you might have heard of people making computers in Minecraft, for example, and for Fortress and Factorial, and even Magic the Gathering, which is a card game, so it's completely like offline. Those are all Turing complete systems, which is kind of cool. But at the same time, with Alan Turing, there was this guy called Alonzo Church who was making his own system for doing computation, which is Lambda Calculus. And it is a very simple and very neat and elegant system. And it has, because it has three things in it. Basically, there are symbols, or variables, to present some values, and there are abstractions, which are function definitions, and applications, which present applying a function to an argument. So this is a very simple and neat system that basically can do every kind of computation you can think of. And the way it can be kind of proven, or, well, we don't go into mathematics here too much, but you know, Church and Turing were working on their own models at the same time, and they found out about each other. And then they discovered that, okay, this other guy is doing also this kind of thing, and wonder what's that about. And then they realized they're actually doing the same thing, just a little bit differently. And they found out their methods are equivalent. So in that sense, you know, anything you can do with Lambda Calculus, you can also do in Turing machines and vice versa. So by conjecture, then, anything you can do with something that is Turing complete in programming languages, you could also do with this Lambda Calculus. And Lambda Calculus is basically the basis for functional programming. So anything you can do in some object-oriented language, you could also do with functional programming by conjecture. Here's a quick look at how this stuff actually looks like. You know, you don't actually have to know this, but basically here the ID is a variable, and we bind this kind of function definition to it. The lambda symbol here means that it's a function. The following x is the parameter, and the dot is basically a separator that separates the function parameters from the body. The body here is just x, so this function just returns the parameter it was given to. And then we have the function application. We apply the function to 1, and since the function just returns what it's given, we get 1 back. So very simple. And yeah, you don't have to actually know this stuff necessarily, but it's good to be aware of it. You don't have to do Lambda Calculus or think about these Turing machines in your daily work life, at all. But, the key here is that there are these good fundamentals that these programming languages have, and that's a good idea to be aware of, I think. And basically the big takeaway is that these two models are equivalent to each other. So when you think about functional programming and if it actually can do anything, then yes, it can do it. Basically what you can do in object-oriented languages or stuff like that. And if you want to know more, there's a good video that I stumbled into, which basically does some Lambda Calculus with JavaScript. And it's really well presented lecture into this stuff. So if you are interested, go check it out. Okay, so functional programming is basically an implementation of Lambda Calculus. We just have like more stuff defined in it already. And this was a thing for me, at least in the beginning, when talking about thinking about this functional programming or idea of functional programming. I mean, all programming languages that I have used have functions. So what's the big deal about that? And in functional programming, we consider the language of functions. It's not like methods in programming language or something like that, but more related to functions in maths. So yeah, and it's fine. It's not that bad. You just basically have to think about it that these functions are pure in the sense that they are only they only consider their parameters when calculating the results, and they're kind of like these black boxes. And for this reason, because it has this kind of maths background, functional programming has been really popular in academia. And but it has also seen rise in industry, and very lately, it's been quite the buzz about it. At least some buzz about it. Some of the most not necessarily popular, but some known functional languages we have here. Lisp, grandfather of them all, and Clojure is based on Lisp. And when we talk about academia, basically Lisp was the original functional language that was used by AI researchers back then. Haskell, one kind of like holy grail of functional programming in a sense. If you have heard of monads, then those come from Haskell. And strongly typed, very robust in that sense. Erlang was made by Ericsson, and it's used in telecommunications. And when you think about it, telecommunications is a field that needs to be very stable and needs to have the software that runs it needs to be reliable. So there might be something into that, but who knows? And then there's stuff like OCaml, Elixir, F#, standard ML, and quite a few others, but I'm not too familiar with those. But there's some. But yeah, especially in financial sector, OCaml and Haskell are quite popular to my understanding. And when you think about, again, reliability and robustness. You know, when you're dealing with a lot of money, that's at least hopefully the thing that's available for the software or the languages that are used in those types of situations. So I don't know, there might be something to that, who knows? So when we compare the two, in functional programming, basically we're concerned with what we want to do, and in imperative or OOP, it's more about the how we do things. So let's say we want to go to a pizzeria and get a pizza, because who wouldn't? And we want the Mexicano pizza. So as a functional programmer, we would just say, okay, we want the Mexicano. And as imperative programmer, we would say we want pizza, and then we put on dough, we put some pepperonis, jalapenos, pineapple, and Mexicano sauce. The way we then achieve these results is a little bit different. When we do functional programming, we basically have data that goes through a series of transformative operations. And when we work on imperative programming, we basically have data, and that is operated by the code. So basically, we have this flow that is a bit like, it's a little bit reversed. In functional programming, we start with Go, and then we just move forward through all the operations with it. And in the end, from the end of the pipeline, we get this pizza that's basically ready. On imperative programming, basically, we have the dough, and then we just add stuff to it. We mutate it, we transform it that way. And so there's a bit of reverse type of flow of how the operations work in these two approaches. And in functional programming, we still have the dough when we are done with the pipeline. So we kind of get the infinite pizza there. But on imperative side, the dough becomes the pizza, so it transforms into something else. And yes, in the end, we have a pizza both ways. It's just slightly different approaches. And here's a little graph about it. You can see on the left side, the functional side, it just is pipeline. And the data is completely like separate from the operations. If you think about something like object-oriented programming on the right side, this all would happen inside some kind of an object. So if you think about replicating this behavior or adding some new behavior, we would have to do something like, okay, this is the Mexicana object. So we want to add opera special object to do opera specials. But when we do functional side, we have no concern like that. We can just take some operations out of the pipeline and replace them with others. So it has this kind of a natural flow of things, and you can have these methods somewhere else and just pick and choose and build your pipelines that way. So it's a little bit different. And like I said, once we are at the end step here where we have the Mexicana pizza, we still have the dough. And that's true for every step here. So once we have done the add pepperoni transformation, we have the result of that. And we take that result and save it somewhere. So if we find out that some of our operations is doing something weird, we can just basically time travel back and see what each step did. And that stuff is available to us. And that's kind of like built into the whole concept of functional programming. On object-oriented side, we would have to build that kind of system ourselves if we want to do some kind of debugging. So if you think about that, okay, that sounds good for free debugging, then yeah, it kind of does. But yeah, so some key functional concepts, if you have heard of this, so let's go through it quickly. There's concept of pure functions. A function's return value is dependent only on its inputs, what you feed the function as parameters. Obviously, if we want to do software that is actually usable, this is not always the case. Basically, the idea would be that if we want to do completely pure software, it would mean that we would like give it some starting parameter, and then it would just pursuit that through all of it and end up with the same result every time, which for software, yeah, it's doable. It's not really useful. So let's just say in practical terms, we want to be as pure as possible, but that's not always the case. Basically, any kind of user input or even output while the program is running would be considered breaking the purity aspect of the function. So to actually make software, we do have to be a little bit impure, but hold to the standard of purity as much as we can. Okay, first class functions. Basically something you might have seen in JavaScript as well. We can pass functions as parameters to other functions. So for example, we could do something like wrap some kind of an event that we want to fire later, pass it on as a function, and when some condition is met, then we fire that. We call that function that was passed to fire the event. So that kind of allows you to do interesting stuff like that. Immutability, once a value is bound, it cannot be changed. So basically, that was what we saw in the Mexicano example. Basically, we have the dough, and it's there, still there, even after we have run through all of our code. And same for basically an application. If we define some kind of a variable in the beginning of the application, it's still available as it is in the end. This is something similar to maybe a const, but not exactly. If you think about a const object, for example, in JavaScript, you can still change the contents of the objects, just not, it's still kind of like the same object is bound to this certain variable, but the insides is what can be changed. Then there's lazy evaluation. Basically, order of execution doesn't matter, and this goes back to the purity aspect, because if we don't have to consider any kind of outside influence to our functions operations, then we can evaluate our functions on a need basis when we actually use them. So this can be something that can save you a little bit of operation time in some cases, but it depends. But yeah, also we don't have like loops in functional programming. We do recursion, because when you think about it, what is a loop in functional programming? It's basically just calling some function again and again, always passing the result down the line. So that's how we handle iteration in functional programming. And then basically here is a summation of the differences. Functional programming, we do immutability. In imperative, we are heavily mutable because we have this kind of some state that we modify on the spot. And recursion is the way out for us to do iteration. In imperative programming, we do loops because, again, we are operating on some kind of an object. So it's more handy to do it by looping some code that then does those operations. And the functions that we strive to write in functional programming are pure, but imperative programming, they are naturally more effectual due to the nature of the imperative programming side. And we have lazy evaluation in functional programming, and imperative programming we have eager. Basically, we need to know what things are, because they might change by some side effect somewhere. And our basic building blocks for functional programming are the functions themselves and symbols. And in imperative side, we have classes or some sort of other similar data structures. So when we talk about functional programming, and object-oriented, for example, obviously there has to be thought of which one is better. And yeah, it kind of depends. Functional code tends to be more bite-sized, and that coupled with purity, we tend to have more testable, more smaller functions, which are more modular. So you can kind of like make them more testable and easily testable, especially when you're making them pure, because then the only thing that affects a function are its parameters. So it's easy to write tests, for example, that only depend on functions parameters. Those are easily testable, and you can always trust that those test cases are running good. So in theory, we have less bugs. No, there's always bugs, always. But in theory, we have less of them. For the object-oriented side, mutations tend to be more performant. So if you're concerned about performance, this is a key thing to think about. We can, in some cases, get close in functional programming, but in general, object-oriented or imperative side is faster. And yeah, immutability is one reason for that. We have to create these all new data structures on every step. For example, back in the Mexicana pipeline, all those steps generate more data structures. So that kind of brings in a performance hit. But it is more safe because we can trust the previous steps, and we can trust that we can do things without affecting the general state of the application. So in that sense, we are more safe when we do functional programming. We don't have to worry about some kind of side effect generally from affecting our application state in some negative way. So that's the thing to consider also. Again, yeah, mutations tend to cause bugs. And once you have a lot of mutations, it can become hard to track where these bugs originate from and how they can actually be fixed. But yeah, computers themselves are more close to how something like Turing machines operate, and so how you program computers in imperative programming is closer to what we do in functional programming. But this again depends on something like a compiler, and the compiler that can do the work for us in bringing us closer to how computers operate. But yeah, functional programming influences are creeping in. So there are modern multi-paradigm languages. There's Scala, there's Kotlin, Rust is one that was influenced by Erlang, for example. And then in many languages, there are influences from functional programming. React has functional components. We have lambdas in Java now, so it kind of creeps in a little bit. Now, let's actually get into what I actually do. And in Solita, we do Clojure. And you might have actually, if you've seen our career pages, you might have seen it. We have something around 20 projects that we have written in Clojure. And I myself am in a full stack Clojure project called Harja. And Harja is open source. You can go make PRs on GitHub if you want. So what is Clojure then? And that's a Lisp variant that operates on top of JVM. And JVM, as we know, it stands for Java Virtual Machine. So Clojure is good because it runs everywhere Java runs, which is 2 billion devices or whatever it is. And JVM itself is very well battle tested. It's been used quite a lot. So it itself is quite a reliable system. And it's also a performance system, despite what people say about Java. It runs well. And because we run on JVM, we can interrupt with Java libraries from Clojure, and we can interrupt with other JVM technologies from Clojure. Stuff like Kotlin and Scala and stuff like that. That's kind of available to us. So there's this massive ecosystem for us to use, which is a nice thing to have. We don't have to build everything ourselves, but we can rely on existing code. And that also brings us to some topic like, if you have heard of the log4j2 issue that we had, that also would impact Clojure projects if you use that kind of logging library there. So massive ecosystem has its pluses and minuses, and that's a good thing to keep in mind. And yeah, if you heard about Lisp, you know that it has a lot of parentheses, and that is true. We like them, and we like to nest them. Another good thing about Clojure is that we have this another tool called Clojure Script, which makes us full stack. Clojure Script is basically Clojure. It just transposed to JavaScript. So we can write front-end code on Clojure. And not only that, but we can do kind of like the same thing that we have on Java side. We can interrupt with JavaScript code. And so there are possibilities there to use like NPM libraries and something like that. If you think about it, that's also really large ecosystem with lots of stuff of different quality that we can use. And because we have this full stack Clojure with Clojure and Clojure Script, we can do stuff like write code once, and then we can use it on both ends of the stack. So that's handy things to use. Obviously, you're not going to do something like write your whole application and just use the same code as a whole, but you can do stuff like utility functions. Let's say you have like some formatting functions that you use because you want to have your data formatted same way, both on the back end and in the front end. So you can write these functions once and then just use them from both the front end code and the back end code. So that's a good thing to have. Okay, so what does it actually look like to write Clojure, or what does the Clojure code look like? So we have this tool we have called REPL. Let's see. Which stands for Read, Evaluate, Print Loop. And it allows us to evaluate code, run code on runtime. So this kind of gives in a little bit of secret. My slide set is actually written in Clojure, and there are a few examples here. Just a little. Here's some Clojure. We have a function call here. Basically, this is an increase function. We give it some kind of numerical value, and then it increases it by 1. So now, when we call it, we get back 2. And then we have some function, which gives us 3, 1 plus 2. And then we get a cider error for some reason, probably. Then we can form strings. And then we have this kind of a when clause here. There's a predicate here that's false. If we would change it to true, then we could add an exclamation mark. Now we get this kind of hello world string. And we do true. And evaluate now, we get a result with an exclamation mark. So this is the way we kind of like nest functions here. We get the result of one function and add it as parameters of the second one. I'm gonna actually. That should help. So we also have the pizza dough here again. This is basically hash. This is called the hash map, and it's basically just like a JavaScript object. It's a key value pair, where the key here is the type, and then we have it has the type of dough. We add it to our namespace, and then we have this is a function definition. We define a function by the name of add pepperoni. It takes one parameter, which is the pizza. And then we do things to the pizza. Basically, the update function here is we take the hash map, we go to the key of ingredients, and we update it via some function. The function here is Koans, which basically takes an array and adds an element to that array. But we call them lists and vectors. And now we can evaluate it. And if we now call the function, we get this data structure that has the type dough, then it has the ingredients key with some pepperoni. And we can nest the function. And now we have a double pepperoni. And if we want to make our Mexicana pizza, we also have a pineapple function, which operates basically the same way. Then we have Mexicana sauce and jalapenos. Now, then we have this kind of threading structure, which basically is just a little bit simpler way to write nested function calls. It basically operates the way that we take the pizza dough here, then we move past the pizza dough to the add pepperoni function. The result of that gets passed to add pineapple function. The result from that, the Mexicana sauce, and so on. And this is basically the same thing as we have here. We have this nested function with all the ingredient functions that we had, and it returns the same thing. It's just a little bit nicer to look at when you have it in this kind of form here. And we can also do many things. Here we define pizza dough. So now when we are changed into the namespace of and check what we have at many drafts. We have this list that has 5 hash maps. And now if we just want to process them all, here we have this kind of composition function, and we just map. If you've used JavaScript, you probably also have used map. So we basically process every item in the list and do this function to them. But yeah, and there we go. We get 5 Mexicana pizzas there. So then we can do stuff like, we can also have filters there. If we want to have like, somebody wants garlic and we only want to make garlic pizzas, then we can do that. We just add a filter into our composition function and we end up with just pizzas with garlic. Here we have a little bit of meta programming, basically, because it gets kind of laborious to do all these pizza pipelines. So we create this kind of a pizza pipeline macro. And this is special in the way that it allows us to dynamically define these functions. So now if we try, we have this create pizza pipeline for an Opera Special, and we add tuna and salami ingredients to it. This will then create for us these add type functions like we have here, the add pineapple one, but it would create functions for add tuna and add salami. But it then would also create us a function called bake and the name of pizza type, which in this case is Opera Special. So we can just call bake Opera Special function and get the pizza out of it. So if we evaluate this macro, then we can try calling add tuna in our REPL here. And it gives us an error because it's not yet defined. But let's go back here. If we do create the pizza pipeline, and now if we try to add tuna, it works. It no longer gives an error to us because it just dynamically inserted these functions to our application while we are running it. So there's some power there that's kind of cool. And like I said, this presentation is also written in Clojure. It's a simple web application, and you can go see it later. Here's the backend side of it. Basically, we run a server here, HTTP server. We are on port 3005. We define some routes to it. We have this routes defined here. It's an API /slide to get a single slide. I just get all the slides. Then we have this ping API, which we can check if we are actually alive. And then my slides here are actually defined here. We have this kind of database thing, which is not actually a real database because I thought no reason to include something like Postgre. But my slides then, they actually look like this. We have these hash maps. again, key value pairs. And then we have vectors, which are like arrays. And I made this kind of a HTML-like language here, where we have these keywords that define what kind of an element I want to display on my slides. And this is a heading, so it turns it into H1 HTML code with this text. Then we have lists, which turns into UL LI list. Quite simple. And but you know, it took me a couple of days to just write this application alongside my normal work hours. But it's actually it works quite well. I'm surprised. And if you look at the front end, this uses Reagent, which is a Clojure Script library that is actually a wrapper on top of React. So if you have used React, there might be some familiar stuff for you here. The difference from React that we have on Clojure Script side is that we don't use something like JSX, but our web pages are defined by this kind of form. It's basically an array of arrays, nested arrays with some keywords here to define what type of HTML element we want to display. But because it is a data structure, it is also easy to manipulate with just normal functions that we have for manipulating data structures. We can get elements from it, and we can add elements to them, you know, simply and programmatically. So that's kind of fun. That's, I think, one of the cool strengths of this kind of this way of doing things, where everything is just data structures and so on. So that's a little bit about the presentation that we have. So okay, we have a little bit of a typo there. REPL is, again, this tool here that we have on the right side of the screen is called the REPL, and it allows me to evaluate code on runtime and just do things like that. And the cool thing about the REPL is that it just not allows us to test code like this or run code like that. We can also access our application state as it's running. I have this slide state atom to hold my application state, and we can not look it because we are not in the right namespace. So we need to change here, and now we can evaluate it, check it. Now we can see that we are at current index 22. There's our history, how we have moved through the presentation, and here we have slide order. Basically, all my slides are defined in this order, and we just go through them one by one. But there was something weird about this slide, because it says that REPL sucks, which is obviously not the case. We need to look at this data on the slides atom. A lot of stuff there. Maybe we need to get our slide state. What was our current index? 22. Okay, so what slide does it correspond to? We get from slide state, and no, we actually do get in slide state and slide order. Okay, so now we know that our slide identifier is the REPL rocks, and that's obviously different than what we have in the slides themselves. So let's see what it says in our slides data. So we get from slides the path of REPL rocks and content. Okay, now we can see the data, how the slide is formed. And obviously that we need to change the heading there. It's wrong. So we do a swap slides. We associate in REPL rocks key, content key. Then we have a vector, so we need to get the first index of a vector, which is 0, and then we get the second index of the nested vector heading REPL sucks, and we just insert there REPL rocks. And now when we go back, oh, my typo there also. But this is just to display that, okay, we can change things on the runtime, which is a really good tool for experimentation and just trying new stuff. You can write functions, try them out with real data, which is really like, cool thing to have. And it's safe. You can test your code in real context of your application and not have to worry about messing things necessarily. Of course, you can if you want to, but if you don't overwrite stuff, you just define your own functions and use them and try them out. You're not going to mess things very likely. So let's see how much time I actually have spent for now. This allows us to do stuff like, we can expand our API very easily because we are running our software. So we know that beer goes well with pizza, so we can expand our API here. We just create new path for our API, and we can define a new function for it. We need to define this handler for it, beer handler. And it takes one parameter, but we're not concerned with that. So we return some kind of a success there. We want to get our beer prices. So we have our olut, which is priced at 60 cents. Then we have our Pirkka olut, which is, I'm not sure, 0.7. Then we have for our more fancier pizza nights, we have our E-Salami Pale Ale at €4. All right. So now we can save that. Let's change our namespace. And actually, now if we try, go to localhost, API ping, we get an OK. So we have an API running. Let's try beer. Nothing. All right. So let's reload our code. Just do it like this. Slide or reload. It's the simple way to do it. If you have a big code base, it might take more time, but now, fingers crossed, we get a response. That's cool. All right. So now we have, written a new API endpoint fairly easily on the runtime, which I think is kind of cool. And we could do things like, add some kind of a post call here. We should be able to do it quite quickly here if we just add div when beer prices slides, then print string beer prices slides. Wow. And then let's add a button that we can click and get beer. Add an onClick event. If you have used JavaScript, this should be familiar. Do Ajax post localhost get my API endpoint beer, and then we add a handler function. Handler and beers swap our slides as sock beer prices with beers. Now, if we do this, we should see something more in our slides. Let's go back. Now we have a get beer button here. If we click this, what happens? All right, now we have our beer display component here, and we can get on with our pizza nights easily, that we know how much our beer costs. And that was a very simple thing to add, and you can add it very dynamically. So I think that's kind of a cool little thing. Let's take it out now, so not to mess up the slides too much. And yeah, then if we want to look at some actual real example, we have Harja, and this is our a feature that I'm working on right now at Harja. You can see there's the same divs, the same HTML elements. Then we have all kinds of cool stuff. We have this kind of a form generator here that does stuff. This is, I'm not going to go too deep into this, but this is what frontend looks like on a real application. And what you get out of that is you get something like this. And we can go and check quickly our test data, and this kind of a form is what comes out of that. So that's fun. I'm gonna reload this because working with React that way sometimes messes the DOM. So what makes Clojure so great, in my opinion? Basically, the REPL makes the development smooth. We can dynamically add stuff. We can modify stuff. We have a lot of control on how we develop things. And as you saw, we can evaluate our code very quickly. We don't have to recompile anything. We can just write new code, evaluate it, and it's ready for us to use. I think that's really strong pro that we have. And it really makes the development experience a lot more fun and a lot more smooth than it might be in some other kind of programming languages where you would have to recompile. This is obviously you have languages where you can hot reload, but this is a little bit smoother because we can just change things directly. And yeah, it enables this very quick, fast feedback loop. And it allows for easy experimentation while you're developing. That's really cool. And you can write, if you write pure functions, you can write any kind of experimental code, and you don't have to worry about, messing something up with like state or something like that. That might happen if you're doing object-oriented code. You might end up with weird bugs because your experimental code does something freaky. But in here, if we don't want to mutate things, we don't have to. So we're pretty safe. And the thing I really like about functional code is that it kind of creates these natural flows of things. Basically, you just put stuff in from point A, and it goes through this pipeline we have and comes out slightly transformed or more transformed. But the flow is there. It basically just goes from point A to point B. And you can modify the flow and tweak the flow, but it still kind of flows naturally. So that makes the development also feel more natural. And writing code makes it feel more natural. And that's because, you are working with data structures. That's all we basically have. Even the code in Clojure is just a data structure. All the stuff we have in here, this whole function is just a list behind the scenes. The first parameter, the first item in the list, which is the defen here, it's basically just a function, and it just sees, okay, this is a list with a function in the first place. So then we run the function that is defined here, and the rest of the items are just parameters to it. So this allows you to do quite interesting things when you get deeper into the meta programming aspect of it, basically changing the code in runtime, which is a really powerful tool that I don't actually myself use too much, but it allows you to do things that are basically impossible in many other languages. You can just modify the code and really expand the language, and the thing about Clojure Code itself is that the code tends to be smaller and modular, which makes it more beautiful. Of course, beauty is in the eye of the beholder, but it makes it more easy to handle and work with. Obviously, functional programming itself and Clojure is a different way of thinking, and getting into it can be hard. But I think once you get into it and you think about these things, it really makes you a better programmer overall. And another interesting thing about Clojure itself is that large parts of the language itself is written in Clojure, so there are no special things there. It's just Clojure code that we use to define more functions on top of itself. And one exercise you could, for example, consider is you take some standard core Clojure functions and implement them yourself, because that's how it is done in the Clojure itself. So you can also do that. So you can still be a better programmer, I think, even if you are not Clojure programmer, by utilizing some functional programming concepts. You know, oh, I have not written that sentence there to completion, but you know, immutability is good practice if performance allows for it. Because again, mutation introduces potential for bugs. So if you don't have to do it, then don't. And write small functions that are easy to test, easy to debug, easy to find out what's wrong with them, easy to read, and easy for others to read also. And you can try to keep your functions pure. Minimize or rather contain any kind of these side effects. So then you know that if something goes wrong and you mutate something weirdly, you know that the culprit is likely in some kind of a, let's say, modify state function or something like that, and you can trace back the bugs that you have created. If your code base otherwise tries to be as pure as possible. And again, yeah, keep any effectful code contained. Like, you know, have, for example, API calls is another one that could be good for this in web development. You know, keep the API calls in their own space and let them be there and just have like an API for that. So then there are a few suggestions for if you want to learn Clojure. Clojure for the Brave and True is a free ebook you can get and read, and I read it back in the day. I'm not sure how relevant it is today, but Clojure as a language doesn't really change that much. It gets stuff added in, but the old stuff doesn't change. So in that sense, basically any book from the recent years is good. For Clojure and TryClojure are online tools that allow you to, they have like these small Clojure practices. You can try Clojure that way and with these small exercises. Clojure Koans is similar, but it requires you to install Leiningen, but then you have these small exercises that you can do locally. If you want to get going, you can get Leiningen. It installs Clojure and it installs the REPL tool for you, so you can start hacking there. And this app, if you want to look at it, it's available on GitHub at that address, if I remember correctly. So aside from Solita, there are a few uses of Clojure in Finland: Metosin, Gofor, Siili, Vincit, Yle, quite a few. That's not all of them, but at least those guys. And here we are. I hope this was informational for you, and hopefully you get some ideas from this presentation. If you have any kind of feedback, then you can reach me on these channels at least. If you want to join our Solita Academia for developers, then I think the newest batch just started, but it should continue. I think twice a year, or maybe.
Twice. Yeah, twice a year.
Yeah. And check our careers pages. If you want tips on your Clojure journey, you can contact me, and I can try to help you. And that's it. Not too much, hopefully, over time.
We don't have any strict time limit, so so no worry about that. Okay, thank you, Jukka. That was quite an interesting presentation. Does any of the listeners do you have any questions for Jukka? Well, I can ask something. Now, if you think about JavaScript programming, that's a typeless language, and Clojure seems to be also typeless, where you move around quite a lot of data to the functions. And in JavaScript, there was always the problem that how do you keep track of that? What is the data structure? What is coming in as a parameter or prop in React or something like this? And the TypeScript was or is some kind of solution for that, at least in a way.
Yeah.
So do you feel that there is the same kind of challenge of keeping track of the incoming data structures in Clojure?
Yes, there can be. And yeah, Clojure is dynamic typing. And there's this kind of weird notion that we have been talking about at Solita with our Clojure programmers, that it usually doesn't introduce as much problems as we would assume. But it is a source of bugs, and it can be also a source of bugs in Clojure projects. There is this feature in Clojure that is optional called spec, which allows you to define this kind of typing system, but it's not, mandatory in the sense that it would be in TypeScript or Haskell or something like that. So you can mitigate those effects also in Clojure, but usually though, when you deal with type issues in Clojure, it's usually just some small things, and because you have like these smaller and purer functions, those don't get spread, and you can quite easily spot those issues and fix them in your development flow.
Right. So for the Clojure script, you mentioned that you can use all the resources from NPM repository, for example. Yeah. So interoperability with JavaScript. How do you find that in practice? It sounds great in theory, but how's that in practice? Is it as easy as it sounds?
It's not as easy as it sounds, because nothing ever is.
Yeah.
There are some I'm not actually sure if we have or how many NPM libraries we have in Harjaprojekti, but I have heard from other projects that getting the NPM libraries to work can be a little bit tricky. There are some other technologies like this JavaScript compiler or builder called Shadow CLJS, which is, to my understanding, made to simplify this kind of process of using the NPM libraries, but I personally haven't used them. So to answer the question, yeah, it's possible in theory, but there might be some cases where it's a little bit more tricky than it might be worth doing. So it's kind of case by case basis, but also the Clojure Script ecosystem also has quite a lot of libraries in itself. So
all right.
It's not really too much of a problem there.
All right. So there is.
But yeah, it's good to be aware of that. It's not always just drop in thing.
Okay. All right. Seems that there are no other questions coming from the audience. So thank you, Jukka, for your presentation, and Kari for this opportunity. It was an interesting presentation for sure. And I have the recording on, so later on I will put this presentation to YouTube, and Kari at least requested the link, so I will send you the link for that, and give the links also for the students in our school, so they can maybe go back if they want to get into details of the, for example, the code presentation part what you made there at the end. Yeah, thank you very much for giving the presentation.
Thank you.
Thank you for having us, and thank you for joining.
Thanks.